Greetings everyone, this is Robert Salute presenting for LAS 568. For today's topic, we'll be taking a look at additive manufacturing, more commonly known as 3D printing. This will include a general overview of what it is, how it works, and the impact the technology has had in different industries. We'll also consider some of the ways the widespread adoption of 3D printing will mean for us in the future in education and in the library. I recently had the pleasure of visiting the Harold Washington Library in Chicago. Home base of the Chicago Public Library, ranked top amongst the public libraries in the U.S. and top 3 internationally by the Heinrich Heine University in Germany. In particular, I had the chance to visit the library's new Maker Lab, an open-access creative workspace equipped with some serious high-tech computer-controlled tools, such as laser and vinyl cutters. Along with this is a set of MakerBot Replicator 2 3D printers. After a brief introduction to the Maker Lab by the supervising staff, along with some negotiating over the lab rules and use of equipment, I managed to reserve some time on one of the MakerBots and print out an object whose digital file I had downloaded from the Thingiverse website. After about a half-hour printing, what I received was a tiny red cube, about 1 inch on all sides, with decorative heart indents on each visible face. It was very lightweight, and the surface finish was imperfect in places, but it was impressively sturdy. However, as small and innocuous as this object was, just moments before it existed in potentia as a tube of plastic and a digital file that someone else had made on the internet. And even though I had neither made the design nor had expended any effort to make the cube beyond commanding the MakerBot to print my file, in some small way I felt that I had printed the object myself and I made it. And so I began to wonder, what kind of impact would 3D printing have, not just for someone like myself, but for everyone? A user with access to a 3D printer and easily obtained software such as Google SketchUp or Makerware can produce a custom-made iPhone case. That very same technology can be used to create affordable prosthetics for amputees. A grade school student can replicate a map of the United States in chocolate, yet that very same process can be tested to create pizza on the International Space Station. Objects can be built as small as a cell, or scaled up to print entire organic-like buildings made of concrete. What we have access to now was once thought to be science fiction, limited to some far utopian future. And now that we see it, the potential for impact is so much larger than we could imagine. Modern additive manufacturing has had its start in the manufacturing industry in the 1980s, where it's seen use in many industries for the purpose of developing product prototypes. Conceptually, the process of 3D printing is a simple one. You take a 3D model made in a program such as AutoCAD into a special program which slices the 3D model into 2D layers, which is then sent to an onboard processor of the 3D printer. The machine then draws each layer one atop the other until the object is then produced physically. The 2D layer drawing process is where the idea of 3D printing comes from. Unfortunately, limitations of processing power, software, cost, speed, accuracy of the replicas, and material flexibility made it hard to move beyond a niche product, let alone something that could be found potentially sitting in a desk or home office. However, now the computing power we have today is many times stronger than it had been a few decades ago, our software more affordable and user-friendly, robotics and materials science is more advanced and ubiquitous, along with the expiration of a few key patents, and especially the collaborative and distributive power of the internet, we now have a whole new industry centered on the proliferation and use of 3D printing by the common person. So let's take a look at a few of the technologies in 3D printing. The first is fusion deposition modeling, or FDM. This is the most common method used by 3D printing in your MakerBots and Ultimakers. It works by pushing material, usually but not limited to plastic, through an extruder nozzle like a hot glue gun. It heats up the printed material to its melting point, at which point the printer begins to draw the layer on a printing bed. As it builds each layer, either the bed or the extruder moves on the vertical axis very slowly, the printer drawing and filling in the slices with each material until the object is finished. Since the FDM process is simple and relatively easy to modify and scale, it's very accessible to the average person. Some can run as low as about $300 for an unassembled kit. On the downside, accuracy is comparatively limited since it has to fight against gravity, and it's difficult to print complex designs without support structures. Then you have stereolithography, or SLA. Rather than adding material to a build plate, it instead solidifies a UV-sensitive polymer such as resin on a bed plate with a sufficiently powerful laser. This method, which is employed on machines such as Formlad's Form 1 printer and the full spectrum lasers Pegasus printer provides greater accuracy down to the 16 micron level and can generate more complex structures since the material in the build platform acts as a support structure itself. Rather than using a laser, some machines such as the B9 Creator use a projector to UV cure the resin, which allows them to create entire layers at once, which makes the process quicker. Selective laser sintering, otherwise known as SLS, works in a similar way, but instead deposits a powder bed of usually plastic material, which is then cured by a high-powered laser instead of a liquid resin. The print quality is a lot higher than FDM, and since the unsintered powder acts as support for the object, porous, complex geometry is more easily created. Compared to FDM, this process is more energy intensive, and the fumes generated by it tends to be toxic. Builds using this method are also limited to a single material. There are many other techniques and technologies that are in 3D printing, such as three-dimensional printing, inkjet and polyjet printing, direct metal laser sintering, and laser engineered net shaping, which all have used different methods but more or less work under the same principles and allow for many different types of applications and materials for any purpose to be built. One interesting to note, however, in January 2014, one of the key patents to selective laser sintering expired and is now available to the public. While it's difficult to predict the actual effects of this, it's worth considering that after Stratasys' patent on FDM printing expired in 2009, we began to see the cheap small-scale desktop printers like the RepRap's Mendel and the first MakerBot printer, which has since snowballed into a whole new transformative industry. So it should be interesting to see what happens in the future. So we see a lot of different interesting things happening, both industry and consumer side. On the industry side, with advancements in 3D printing, many fields are making use of the ability not just to design and print prototypes on demand, but create really unique, customized parts with equally unique properties. In the medical field, for example, hospitals can use CT scans to create 3D digital CAD files of a person's body and internal structure, and from there print out prosthetics such as hip or spinal implants that are lighter, stronger, and have a lower chance of rejection by the immune system. In one particular case on February 29, 2012, Dr. Glenn Green of the University of Michigan custom printed a polycapritone tracheal splint to treat a newborn's critical respiratory condition. This saved the child's life, and that child has been living well for over a year. Manufacturing is also making pretty impressive strides incorporating 3D printing into their production, not just using 3D printing for rapid prototyping purposes. The ability to create metal parts with complex internal structures has led to unique designs in the automotive and aerospace industries that cannot be replicated through traditional manufacturing. One company, for example, Core Ecologic, their Irby and Irby 2 automotive vehicles, for example, make significant use of FDM technologies to create a fuel-efficient car, which they plan to drive across the United States in one single 10-gallon tank of gas. Not only is the chassis 3D printed, but for the Irby 2, a majority of its internal parts and structures are created with the additive manufacturing process. 3D printing has been adopted in many other fields and industries besides. Fashion designers have used 3D printing to create clothing with intricate design structures such as a woman's wedge heel shoe with a geometric wire lattice. Enrico Dini's D-shaped printer, conversely, is capable of printing house-sized building structures by using concrete, artificial sandstone, or one day moon dust. While industrial printers and its applications have become more advanced and pronounced, 3D printers are rapidly becoming cheaper and more advanced than ever. Printers like the RepRap Prusa Mendel, the PrinterBot, MakerBot Replicator 2, and Lulzbot Taz have all allowed for educators, hackerspaces, design offices, and regular people to access 3D printer technology for well under a $10,000 entry price point that are normally associated with commercial machines. Users have so far produced a variety of objects from pens to microcontroller cases, figurines, mechanical puzzles, and even fully articulated robots. And thanks to the internet, there are several dedicated hubs such as Thingiverse, where digital blueprints are stored and made available to the public. 3D printing companies such as Shapeways have allowed the sharing model to be monetized by allowing designers to sell prints of their designs on the marketplace. Their accessibility of the design and creation tools, combined with the global support network of the web, has opened up a wide field of possibility and inspiration for creators. As 3D printing becomes more advanced, the machines available to the public will be easier to use and maintain, allow for more versatile and accurate products, and allow for more and varied unique materials at an affordable price. Let's consider another field where 3D printing has the power to transform: Education, particularly in STEM fields, has become more important in sustaining an economically viable and competitive nation and closing the income disparity gap. The Obama administration has invested over $4.3 billion in the Race to the Top program and is training 100,000 new K-12 STEM educators by the next decade. The application of 3D printing in this classroom has the potential to provide an element of tangible, active learning to the curriculum as students create and interact with the lessons in a physical way. Here's an example. As part of the Fab at School program designed by Dr. Glenn Bull, grade school students are given a chance to utilize desktop additive manufacturing and simplified design software to actively engage in engineering projects. In one instance, 2 girls were developing their own wind turbine, which is meant to power a small light bulb. Given this task, the students actively engaged in analyzing the issues as they developed. In this case, they successfully found that their circuit was incorrectly designed after physically disassembling their work. In this way, we see how 3D printing and accessible fabrication technology can be used in the classroom, not just learning concepts of engineering design, but actively engaging in the lesson through application. So, taking all this into account, we can see the potentially disruptive and transformative nature of 3D printing in a variety of industries. The attraction of publicly available 3D printing is undoubtedly powerful. The barriers between design and production have narrowed significantly, and it's getting easier and more accessible to distribute your creations as well through the internet. We are coming upon a time where not only anything can be created, but anyone can be a creator. But what does this mean for libraries themselves? Undoubtedly, using the novelty of 3D printing can be a method to attract visitors to our library services. Many libraries already have spaces built to encourage creativity in our younger patrons, with tools, instruments, and software normally out of reach to the average teenager. But does the potential novelty justify the investment? Well, in truth, the library has always been a place where technology that supports community is at the forefront. Patrons not only borrow books and magazines, but use computers to access the internet all the time. And not only that, but we have e-readers, tablets, and laptops, and many other technologies normally out of financial reach or convenience of its patrons, which are available for cheap or free access. Supporting 3D printers, which are becoming more and more prominent and accessible, should be no different than having a computer and internet. Back in the Maker Lab of Harold Washington Library, as I was learning and printing my own cube on the MakerBot, I watched as patrons approached the lab supervisors, peppering them with questions. What is this? How was this object made? How does this work? What happens if I try to print this? And the supervising librarians, ever busy, not only answered their questions cheerfully, but encouraged each patron to try and make something for themselves. The library mission has always been about not only satisfying curiosity, but encouraging it. And if 3D printing in the library inspires that kind of curiosity and creativity, what other reason do we need to welcome it? So here's a few questions. Would you consider 3D printing to actually be a disruptive technology, or would you consider it just a fad and novelty that is just getting its time in the light? What other industries and disciplines can you see having 3D printing in its place? And if you have a machine that could create anything you imagined, what would you make? Here are the ways I applied the ARCS model for this presentation. For attention, I personally explored a library makerspace and presented the experience of 3D printing firsthand. For relevance, I brought the discussion of various applications of how 3D printing technologies are used and how it may develop in the future. Confidence, I explained the technology of 3D printing, terminology, how current devices work, and what currently is and isn't capable of achieving. And with satisfaction, I presented questions for discussion on the topic of 3D printing, and how and if it may be utilized in the future and in our own lives.